The final countdown begins 14 days. That is all we have left. In exactly 14 days, on December 19th, 2025, an object older than our sun, older than every rock and river and living thing that has ever existed on this planet, will make its closest approach to Earth. And right now, at this very moment, as you listen to these words, telescopes across the world and spacecraft scattered throughout the solar system are watching it. They are watching 3i Atlas creep closer. They are watching its twin tails shimmer against the blackness. They are watching for something, anything, that might finally answer the question that has consumed the scientific community for 5 months. Is this thing a comet or is it something else entirely? Because here is what nobody is telling you. The anomalies are not going away. They are multiplying, and the window to understand what we're dealing with is closing faster than anyone wants to admit. By the time this visitor slips past us and begins its long journey toward Jupiter, we will either have our answers, or we will spend the rest of human history wondering what we missed. Before we dive in, if you find value in what we explore together, if these deep dives into the mysteries of our cosmos keep you coming back, take a moment right now to hit that like button. And while you are there, if you have not already, subscribe and turn on notifications so you never miss an upload. We have been tracking this interstellar visitor since July 1st, when the Atlas telescope in Chile first spotted it, hurtling through the outer reaches of our solar system. You already know the basics. You know it is the third confirmed interstellar object in recorded history, following Oumuamua in 2017 and Borisov in 2019. You know it originated from somewhere beyond our solar system, possibly from the thick disk of the Milky Way, making it potentially 7 billion years old. You know it passed behind the Sun in late October, survived its perihelion on October 29th, and emerged on the other side still intact, still active, still baffling researchers with behaviour that does not quite fit the textbook definition of a comet. But what you may not know is what has happened in the last 72 hours, and this is where things get interesting. On December the 4th, 2025, a wave of new data hit the scientific community simultaneously from multiple sources. NASA released fresh Hubble images showing 3i Atlas in unprecedented detail. The European Space Agency published a teaser image from their JUICE spacecraft, and that image alone has sparked debates that are still raging across academic circles and social media alike. Meanwhile, a preprint study posted just days ago claims to have found evidence of cryovolcanism, ice volcanoes, erupting from the surface of this ancient wanderer. Think about that for a moment. Ice volcanoes on an object that has been drifting through the frozen void between stars for billions of years. Now suddenly, as it passes through our little corner of the galaxy, it awakens, it erupts, it puts on a show. Coincidence? Perhaps. Or perhaps we are witnessing something we do not yet have the framework to understand. Let me walk you through what the next 14 days look like, because if you have any interest in observing this object yourself, if you want to be part of this historic moment, you need to understand the timeline we are working with. Right now, as of today, December 5th, 3i Atlas is positioned in the constellation Virgo, visible in the pre-dawn sky for those of you in the Northern Hemisphere. It is rising earlier each night, climbing higher above the horizon, and by the time we reach December 19th, it will have migrated into Leo, sitting almost directly beneath the bright star Regulus. That is your landmark. That is your guide. If you can find Regulus in the eastern sky before dawn, you are looking in the right direction. But here is the catch. You will not see it with your naked eye. This is not a spectacular naked eye comet like some we have witnessed in the past. At its closest approach, 3i Atlas will still be 170 million miles away from Earth. That is nearly twice the distance between Earth and the Sun. To put that in perspective, when the Moon appears in our sky, it is roughly 250,000 miles away. 3i Atlas will be almost 700 times farther than the Moon at its closest point. So while it poses absolutely no danger to our planet, it also means you will need equipment to see it. NASA recommends a telescope with at least a 30-centimetre aperture, roughly 12 inches, to have a realistic chance of spotting this visitor. Smaller telescopes might catch a faint smudge under ideal conditions, but for most backyard astronomers, this will require either excellent equipment or participation in one of the many live observation events being hosted by institutions around the world. The Virtual Telescope project, based in Italy, has already announced a live feed scheduled for December 19th at 4 in the morning Universal Time. They will be pointing their remotely operated telescopes directly at 3i Atlas and streaming the view for anyone who wants to witness history from the comfort of their home. But let us pause here and address the elephant in the room, because you did not come here just to learn about telescope specifications and viewing angles. You came here because something about this object does not add up. You came here because you have heard the whispers, the theories, the increasingly uncomfortable questions that mainstream science seems reluctant to answer. And the truth is, those questions deserve to be asked. Consider the trajectory. 3i Atlas is travelling in near-perfect alignment with the ecliptic plane, the flat disk where all the planets orbit our Sun. The odds of a random interstellar object arriving at precisely this angle are roughly 1 in 500. That alone raised eyebrows when it was first calculated. But then researchers noticed something else. The object made suspiciously close passes to Mars, Venus, and will soon approach Jupiter within a distance that matches almost exactly with Jupiter's Hill radius, the gravitational boundary where a planet can capture satellites. The combined probability of all these alignments occurring by chance has been calculated at roughly 1 in 20,000. Now, does that prove anything? Of course not. Improbable events happen all the time. Someone wins the lottery every week, despite odds of millions to 1. But when improbabilities begin stacking on top of each other, when the anomalies multiply rather than resolve, the scientifically honest response is to keep asking questions. Harvard astrophysicist Avi Loeb has been cataloguing these anomalies since the beginning. As of this week, his count has reached 13 distinct features of 3i Atlas that do not fit neatly into our understanding of typical cometary behaviour. We will explore each of these in detail as this documentary unfolds, but for now understand that the list includes everything from its unusual chemical composition, with far more nickel than iron, to its anti-tail that points toward the Sun rather than away from it, to the non-gravitational acceleration it exhibited at perihelion that cannot be fully explained by outgassing alone. Loeb has developed what he calls the Loeb scale, a 10-point rating system for anomalous interstellar objects. A 0 means definitively natural, a 10 means definitively technological and potentially threatening. As of his most recent assessment, 3i Atlas sits at level 4, meaning it exhibits anomalies that meet potential technosignature criteria. He has stated publicly that he assigns a 30 to 40% probability that this object does not have a fully natural origin. Let that sink in. One of the most prominent astrophysicists at one of the most prestigious universities in the world is saying there is roughly a 1 in 3 chance that what we are watching approach our planet is not a comet at all. Now, to be absolutely clear, the overwhelming consensus among mainstream astronomers is that 3i Atlas is exactly what it appears to be, an ancient chunk of ice and rock from another star system, doing exactly what comets do when they get close to a star. NASA has stated unequivocally that it looks and behaves like a comet. ESA agrees. The vast majority of planetary scientists agree. They point to the presence of a coma, the fuzzy halo of gas and dust surrounding the nucleus. They point to the spectral signatures showing water, carbon dioxide, and other volatiles sublimating from its surface. They point to behaviour that, while unusual in some respects, falls within the broad range of what we have observed from other comets, and they may be completely right. But here is what troubles me, and perhaps it troubles you too. Throughout history, scientific consensus has been wrong before. Not often, but enough times to matter. The scientists who dismissed continental drift, the physicians who laughed at the idea of washing hands between patients, the astronomers who insisted the Sun orbited the Earth. Consensus is valuable. It represents the best current understanding of accumulated evidence, but it is not infallible, and when anomalies persist, when they multiply, when they refuse to be explained away, the proper response is not to double down on certainty. It is to remain curious. It is to keep looking. That is what we are going to do together over the next 2 hours. We're going to look. We're going to examine every piece of evidence, every theory, every whisper and rumour, and carefully documented observation. We're going to prepare ourselves for December 19th, not just as passive observers, but as informed participants in one of the most significant astronomical events of our lifetime. Because regardless of whether 3i Atlas turns out to be a billion-year-old comet or something far stranger, one thing is certain: we will never see it again. This visitor is moving too fast to be captured by the Sun's gravity. After its closest approach to Earth, it will swing past Jupiter in March of 2026 and then disappear back into the interstellar void from which it came. Whatever it is, whatever secrets it carries, this is our only chance to learn them. So the question becomes, how do we prepare? What equipment do we need? What should we look for? What observations might reveal something that automated systems miss? And perhaps most importantly, what signs would indicate that this is more than just a comet, and what signs would confirm that it's exactly what mainstream science believes it to be? These are the questions we will answer. But first, we need to talk about the ice volcanoes, because what researchers discovered in the days following perihelion has changed everything we thought we knew about how this object behaves. And if those findings hold up under scrutiny, they may offer the first real clues about what 3I Atlas is made of, where it came from, and why it is putting on such an extraordinary show as it passes through our cosmic neighbourhood. The spiral jets have been photographed, the cryovolcanic plumes have been documented, and what they reveal about the interior of this ancient traveller is nothing short of extraordinary. Preparing your eyes for the interstellar guest. The pre-dawn sky in December carries a particular kind of silence. If you have ever stood outside in those hours before sunrise, wrapped against the cold, watching the stars slowly fade as the horizon begins to glow, you know what I mean. There is a stillness to it, a sense that the universe is holding its breath, and over the next 2 weeks that silence will be broken by something extraordinary. An object that has travelled for billions of years across the emptiness between stars will reach its closest point to our planet, and if you know where to look, if you have prepared properly, you can witness it with your own eyes. But preparation is everything. This is not the kind of event where you can stumble outside at any random hour and expect to see something spectacular. 3I Atlas demands effort, it demands patience, and it rewards those who come prepared with an experience that connects them to something ancient and unknowable in ways that few astronomical events can match. So let us talk about what you actually need to do. First, understand the timing. 3I Atlas is a morning object right now and will remain so through its closest approach. This means you need to be outside before dawn, ideally at least 2 hours before sunrise when the sky is still fully dark and the comet has climbed high enough above the eastern horizon to clear any atmospheric haze or light pollution. For most observers in the northern hemisphere, this translates to viewing windows between roughly 3 and 5:30 in the morning local time. Yes, that means setting an alarm. Yes, that means losing sleep. But consider what you are waking up for. You are waking up to see something that formed around another star, possibly before our own sun even existed. You're waking up to witness a messenger from the deep past, a time capsule from a solar system we will never visit, carrying chemistry and secrets from an epoch so remote that our entire civilization is less than a heartbeat by comparison. Now, about equipment. I mentioned earlier that NASA recommends a telescope with at least a 30cm aperture for reliable observation. But let me give you a more nuanced picture, because the reality is more encouraging than that guideline might suggest. If you own a telescope in the 8 to 10 inch range, roughly 20 to 25 centimeters, you have a fighting chance of spotting 3I Atlas under excellent conditions. The key variables are sky darkness, atmospheric stability, and your own experience as an observer. A seasoned amateur astronomer with an 8-inch Dobsonian under truly dark skies might pick out the comet as a faint fuzzy patch, especially if they know exactly where to look and have trained their eyes to detect subtle contrast differences. Meanwhile, someone with a 12-inch telescope observing from a light-polluted suburb might struggle to see anything at all. This brings us to the most important factor in your preparation, and it has nothing to do with equipment. It is about knowing your observing site. If you are serious about seeing 3I Atlas, you need to scout locations now. Not on December 18th, now. Drive out of town if you have to. Find a spot with clear views to the east, away from city lights, away from street lamps and illuminated signs. Check the horizon carefully. Are there trees or buildings that will block your view at low elevations? Remember, in the days leading up to closest approach, the comet will be rising in the east and climbing through Virgo and into Leo. You want an unobstructed view of that part of the sky. Use a light pollution map. There are several excellent ones available online for free. They will show you exactly how dark the skies are in your area and help you identify the nearest dark sky sites. Even driving 30 minutes outside a major city can make an enormous difference in what you can see. Now, for those of you who do not own a telescope, or whose equipment is not quite up to the task, do not despair. You have options. The first and most accessible option is to join an organised observation event. Astronomy clubs around the world are planning viewing sessions for 3i Atlas. Many observatories, both professional and amateur, will be hosting public nights where you can look through large telescopes guided by experienced observers. Check with your local planetarium, your nearest university astronomy department, or search online for astronomy clubs in your region. These events are typically free or very low cost, and they offer the additional benefit of community. There is something special about standing in a field with fellow enthusiasts, taking turns at the eyepiece, sharing the experience of witnessing something that none of us will ever see again. The second option is virtual observation. The Virtual Telescope project has been at the forefront of bringing astronomical events to global audiences, and they have already announced their plans for December 19th. Starting at 4 a.m. Universal Time, they will stream live views of 3i Atlas through their remotely operated telescopes in Italy. You can watch from your phone, your tablet, your computer. You can see it in real time with commentary from professional astronomers explaining what you're looking at. Is it the same as being there in person? No, but it is infinitely better than missing it entirely. And there is a third option that has emerged in recent years, one that sits somewhere between traditional telescopes and pure virtual observation: smart telescopes. Devices like the C-Star S50 and similar products have revolutionized amateur astronomy by combining small aperture optics with sophisticated image processing. These telescopes automatically locate objects, track them as they move, and stack multiple exposures to reveal details invisible to the naked eye. Several observers have already captured images of 3i Atlas using these devices, proving that you do not necessarily need a massive traditional telescope to participate in this event. In fact, one of the remarkable stories emerging from the 3i Atlas observations is how amateur astronomers with relatively modest equipment have sometimes produced clearer images than those released by major space agencies. We will talk more about that controversy later, but for now, understand that the democratization of astronomy means you have more tools available to you than any previous generation of stargazers. Let me give you specific coordinates and landmarks for locating 3i Atlas over the next 2 weeks. As of December 5th, the comet is located in the constellation Virgo, not far from the star Zaviava, also known as Beta Virginis. If you're familiar with finding Virgo in the sky, you can use the bright star Spica as a starting point and work your way north. The comet is moving relatively quickly against the background stars, so its position will shift noticeably from night to night. By December 12th, 3i Atlas will have moved closer to the border between Virgo and Leo, passing near a faint spiral galaxy called NGC 4536. You will not see the galaxy without a fairly large telescope, but it serves as a celestial waypoint for those using detailed star charts. By December 19th, the night of closest approach, the comet will be in Leo, positioned almost directly below Regulus, the brightest star in that constellation. Regulus is easy to find. It sits at the base of the backwards question mark asterism that forms the head of the lion. If you can locate Regulus, you're within a couple of degrees of 3i Atlas. For precise coordinates on any given night, I recommend using planetarium software or mobile apps that can calculate the comet's position for your specific location and time. Programs like Stellarium are free and extremely accurate. Simply input the comet's designation C2025-1, and the software will show you exactly where to point your telescope. Now, let us talk about what you might actually see. At its current brightness, 3i Atlas is hovering around magnitude 11, which places it well beyond naked eye visibility, but within reach of moderate amateur telescopes. As it approaches Earth, it may brighten slightly, perhaps reaching magnitude 10, or even a bit better under optimal conditions. Through a telescope, it will appear as a small fuzzy patch of light, distinctly different from the sharp pinpoints of stars. If you're using enough aperture and the sky's dark enough, you may detect hints of the coma, the cloud of gas and dust surrounding the nucleus. With larger telescopes or long exposure photography, you might even glimpse the tail. But here is where I want to manage expectations carefully. 3i Atlas is not going to look like the spectacular comet photographs you see online. Those images are created by stacking many exposures and processing them to reveal faint details. Through the eyepiece of a telescope in real time, comets are almost always subtle objects. They're ghostly. They require patience and dark adaptation to fully appreciate. That said, there is something profound about seeing it live that no photograph can capture. When you look through a telescope at 3I Atlas, the photons striking your retina left that object roughly 15 minutes earlier. You're seeing ancient light reflected from a surface that has been travelling through the void since before the first humans walked upright. There is a directness to that experience, a connection to cosmic timescales that transforms a faint smudge into something transcendent. Spend time with it. Do not just glance and move on. Let your eyes adapt. Let the reality of what you are seeing sink in. This is not a photograph. This is not a simulation. This is an actual piece of another solar system, billions of years old, passing through our neighbourhood at 150,000 miles per hour, and you are watching it happen. For those of you planning to photograph the comet, the techniques vary depending on your equipment. If you have a DSLR or mirrorless camera and a tracking mount, you can capture surprisingly detailed images by stacking multiple exposures. Start with individual frames of 30 to 60 seconds at high ISO, then combine them using stacking software like Deep Sky Stacker or Sequator. The key is to track on the comet itself, not the background stars. This will render the comet sharp while trailing the stars, but that is actually a visually striking effect that emphasizes the motion of this interstellar visitor. If you are using a smart telescope with built-in stacking capabilities, simply point at the coordinates, let the device work its magic, and watch as the comet gradually emerges on your screen over several minutes of integration time. Document your observations. Write down the time, your location, the equipment you used, and what you saw. Note the shape of the coma, any hint of tail structure, the overall brightness compared to nearby stars. These records may seem trivial in the moment, but they contribute to the collective understanding of this object. Amateur observations have historically played crucial roles in comet science, and with 3I Atlas presenting so many unusual characteristics, every pair of eyes matters. And pay attention to the unexpected. If you notice anything unusual, anything that seems out of place or different from what you expected, document it carefully. Take notes. Take photographs if you can. The anomalies surrounding 3I Atlas have been reported not just by professional observatories, but by amateur astronomers around the world. You might see something significant without even realizing it. Which brings us to those anomalies. 13 of them now, according to Professor Loeb's latest count. Each one small enough to dismiss individually, each one explainable by some natural process. But taken together, they form a pattern that refuses to resolve into comfortable certainty. And the most visually striking of these anomalies, the one that has generated the most debate in recent weeks, involves something that should be impossible according to standard cometary physics: the anti-tail, the jets that point toward the sun instead of away from it, and the spiral structures within the coma that suggest rotation patterns never before observed in any comet. To understand why these features matter, to understand why they have some researchers quietly updating their probability estimates for a non-natural origin, we need to dive deep into the 13 anomalies that refuse to disappear. The 13 anomalies that refuse to disappear. Science works by pattern recognition. We observe the universe, we note regularities, we build models that predict what should happen based on what has happened before. When those predictions match reality, we gain confidence in our understanding. When they do not, we face a choice. Either our observations are flawed or our models are incomplete. With 3I Atlas, our models keep coming up short, not by much, not in ways that scream artificial origin, but in subtle, persistent ways that add up to something that demands attention. Let me walk you through all 13 anomalies that Professor Avi Loeb and his colleagues have catalogued. I want you to understand each one on its own terms before we consider what they might mean collectively. Because individually, every single one of these can be explained by natural processes. That is not the point. The point is whether natural processes should produce all of them, in combination, in a single object. Anomaly number 1, the orbital alignment. 3I Atlas is travelling within 5 degrees of the ecliptic plane, the flat disk where all the major planets orbit our Sun. For a random interstellar object arriving from any direction in 3-dimensional space, the probability of this alignment is roughly 1 in 500. Not impossible. Not even terribly unlikely for a single object, but notable. Anomaly number 2, the retrograde trajectory. Unlike nearly all objects in our solar system, which orbit the Sun in the same direction the Sun rotates, 3I Atlas is moving backwards. it is travelling against the flow. This retrograde path is relatively rare but not unprecedented for interstellar visitors. Borisov also had a somewhat retrograde trajectory. However, the specific geometry of 3I Atlas's retrograde orbit is particularly well suited for deploying probes to inner solar system planets, if one were inclined to think in those terms. Anomaly number 3, the planetary close approaches. 3I Atlas passed within 29 million kilometres of Mars on October 3rd. It will come within roughly 50 million kilometres of Jupiter in March of 2026, and that Jupiter distance is not random. It matches, almost precisely, Jupiter's Hill radius, the gravitational boundary where a planet can capture moons or satellites. The probability of hitting that specific distance by chance has been calculated at 1 in 26,000. Anomaly number 4, the size mystery. Estimates of 3I Atlas's size have varied wildly throughout its observation period. Initial calculations suggested a nucleus potentially 20 kilometres across, making it vastly larger than either Oumuamua or Borisov. More recent Hubble observations constrain the upper limit to about 5.6 kilometres, but the lower limit could be as small as 440 metres. This enormous uncertainty is itself unusual. For most comets, we can pin down the size with much greater precision by observing how much light they reflect. Anomaly number 5, the extreme mass. Based on the amount of material being ejected, 3I Atlas appears to have a minimum mass of 33 billion tons, roughly 1,000 to 1 million times more massive than Oumuamua or Borisov. If accurate, this makes it an extraordinary outlier among interstellar objects. We would not expect to encounter something this massive as our third detection. Anomaly number 6, the nickel to iron ratio. Spectroscopic analysis has revealed that 3I Atlas contains far more nickel than iron in its emissions. This ratio is unusual compared to most solar system comets, though not entirely unprecedented. What makes it interesting is that nickel-heavy compositions are more commonly associated with industrial alloys than natural space rocks. I want to be clear that this does not prove anything artificial. Nature produces all sorts of unusual chemical ratios, but it adds another data point to the growing list of oddities. Anomaly number 7, the extreme negative polarization. When light reflects off a surface, it becomes polarized in ways that reveal information about the surface texture and composition. 3I Atlas shows negative polarization values more extreme than any comet ever measured. This suggests surface properties unlike anything we have seen before in our solar system. Anomaly number 8, the anti-tail. This is perhaps the most visually striking anomaly, and the one that has generated the most debate. Normal comet tails point away from the sun because solar radiation pressure pushes dust and gas outward. But 3I Atlas has displayed a prominent feature pointing toward the sun, first observed in July, again in August, and most recently in November after it emerged from perihelion. While anti-tails can occur naturally due to geometric viewing effects and large dust particles, the persistence and intensity of this feature have raised questions. Anomaly number 9, the brightness behaviour. As 3I Atlas approached perihelion, it brightened faster than predicted by standard cometry models. It also appeared bluer than the sun, which is unusual for a typical dusty comet. These photometric anomalies suggest either unusual surface composition or unusual emission mechanisms. Anomaly number 10, the survival of perihelion. Many hoped that the comet's closest approach to the sun would provide clarity. The intense heating, roughly 770 watts per square metre, was expected to potentially fragment a loosely bound cometary body. Instead, 3I Atlas emerged intact, apparently unfazed by its solar encounter. While comets certainly can survive perihelion, the combination of high activity and structural integrity is noteworthy. Anomaly number 11, the non-gravitational acceleration. This is where things get technically fascinating. As 3I Atlas passed through perihelion, tracking data revealed that it was not following a purely gravitational trajectory. It was accelerating slightly in ways that cannot be explained by gravity alone. Now this is actually common for comets. Outgassing acts like tiny rocket thrusters, pushing the comet off its expected path. But the specific pattern of acceleration observed in 3I Atlas, with both radial and transverse components, is more complex than typical cometary outgassing would predict. Anomaly number 12, the rotation signature. Recent high-resolution images have revealed spiral structures within the coma, suggesting that the nucleus is rotating in ways that produce distinctive patterns in the ejected material. More intriguingly, some observers have reported what appear to be dual clockwise spin waves, structures that would require a remarkably stable internal axis and consistent material ejection. No natural comet has ever displayed this particular pattern in the historical record. Anomaly number 13, the Jupiter trajectory. This is the newest anomaly, identified just weeks ago. When you trace 3I Atlas's path forward, it will pass Jupiter at a distance that matches the planet's hill radius with an accuracy of 0.06 million kilometers. This is the exact distance at which a spacecraft could perform an optimal Oberth maneuver, using Jupiter's gravity to brake or accelerate while minimizing fuel expenditure. The probability of this precise alignment occurring by chance is approximately 1 in 26,000. Now, let us step back and consider what we are looking at. Each of these anomalies, taken individually, has a natural explanation. Orbital alignments happen by chance. Retrograde trajectories occur. Chemical compositions vary. Anti-tails are known phenomena. Non-gravitational acceleration is standard for active comets. Any scientist can point to each item on this list and say, yes, that is unusual, but it is not impossible for a natural object. And they would be right. The question is not whether each anomaly can be explained naturally. The question is whether the combined probability of all 13 occurring together in a single object is consistent with our expectations for random interstellar visitors. Professor Loeb has attempted to calculate this combined probability. His estimate, which is admittedly rough and subject to significant uncertainty, suggests odds of less than 1 in 10 billion that all these features would occur together by chance in a natural object. Now, that calculation involves assumptions that other scientists dispute. The anomalies are not all independent. Some may be correlated in ways that affect the statistics, and we have only observed 3 interstellar objects, which is far too small a sample size to make confident probability claims. But here is what troubles even skeptical researchers. The anomalies are not resolving as we gather more data. They are multiplying. Each new observation period adds another entry to the list rather than crossing existing entries off. That is not the pattern you expect when dealing with an unusual but natural object. Normally, as we study something longer and more carefully, the mysteries shrink. With 3I Atlas, they grow. The mainstream scientific position remains that all of this can be explained by invoking an interstellar comet with unusual but natural properties. And that position is defensible. We have only seen 3 interstellar objects. Our expectations for what such objects should look like are based on models that may not capture the full diversity of what is out there. Perhaps 3I Atlas is simply the first representative of a class of interstellar bodies we have not encountered before. Perhaps billions of years of cosmic ray bombardment and thermal cycling in interstellar space produce surface properties and compositions that we have never observed in our own solar system's comets. This is the position of researchers like Penn State astrophysicist Jason Wright, who has systematically addressed each of Loeb's claimed anomalies in detailed blog posts. Wright argues that planetary scientists understand comets are highly variable objects. He invokes the old saying that comets are like cats. They have tails, and they do precisely what they want. No 2 comets behave identically, and we should expect an interstellar comet to be even more unpredictable than local ones. It is a reasonable argument. It may even be correct. But it does not explain the spiral jets. It does not explain why the anomalies keep accumulating rather than resolving. And it does not address the fundamental question of how we would recognize something artificial if it were designed to look natural. Consider the possibility, just as a thought experiment. If an advanced civilization wanted to send a probe to another star system, what would be the optimal design? Would they send something obviously artificial, a gleaming metal spacecraft beaming radio signals in all directions? Or would they disguise their probe as a natural object, a stealth hybrid that could observe without being recognized, slipping through foreign systems under cover of cosmic mundanity? The Trojan horse hypothesis, as some have called it, suggests that the absence of obvious artificial signatures is not evidence against technological origin. It might be evidence of sophisticated design. I am not saying 3I Atlas is an alien probe. The balance of evidence still favours a natural explanation. But I am saying that dismissing the anomalies without serious consideration is not science. It is faith in our existing models. And faith, however comfortable, is not how we make discoveries. What we need is data. More data, better data. And fortunately, that is exactly what the next 2 weeks will provide. The Hubble Space Telescope reobserved 3I Atlas on November 30th, and new images are being processed as we speak. The James Webb Space Telescope is scheduled for additional observations in December. Ground-based observatories around the world are dedicating time to this target, and amateur astronomers, equipped with increasingly sophisticated tools, are contributing observations that sometimes exceed what professional facilities provide. But perhaps the most intriguing data is not coming from Earth at all. It is coming from a spacecraft currently en route to Jupiter, a spacecraft that observed 3I Atlas from a unique vantage point just after perihelion, and whose preliminary images have already sparked intense debate. The European Space Agency's JUICE mission was not designed to study comets. It was designed to study the icy moons of Jupiter. But when 3I Atlas appeared in our solar system, mission planners realized they had an unprecedented opportunity. A chance to observe an interstellar visitor during its most active phase, from a perspective unavailable to any Earth-based telescope, and what JUICE saw has changed the conversation entirely. Because in that single teaser image, released just days ago, 3I Atlas displays not one tail but two, and the implications of that dual-tail structure are still being debated by researchers around the world. Ice volcanoes from another star. On December the 1st, 2025, a preprint appeared on the Scientific Archive server that would reshape how we understand this interstellar visitor. Researchers using the Joan Oro telescope in Spain had been meticulously photographing 3I Atlas as it emerged from its closest approach to the Sun. What they found in those images was not what anyone expected. Spiral jets of gas and dust were erupting from the comet's surface in patterns that suggested cryovolcanism, ice volcanoes, active geological processes driven not by molten rock, as on Earth, but by the violent sublimation of frozen volatiles exposed to solar heating for the first time in billions of years. Think about what this means. 3I Atlas has been drifting through interstellar space at temperatures approaching absolute zero for longer than our solar system has existed. Its interior has been frozen solid, pristine, unchanged since it was ejected from its home system around a star we will never identify. And now, suddenly, as it passes through our cosmic neighbourhood, that ancient ice is erupting. We are watching a piece of alien geology come alive. The researchers behind this discovery, led by Josep Trigo Rodriguez, proposed a specific mechanism for what they observed. As the comet approached the Sun, its surface temperature began to rise. When it crossed the threshold at which solid carbon dioxide, dry ice, transitions directly to gas, that sublimation opened pathways into the comet's interior. An oxidizing liquid began to flow through cracks and fissures, reacting with metallic grains of iron and nickel sulfides that had been locked in the pristine matrix for eons. The result was explosive outgassing in discrete jets, focused eruptions that spray material into space in patterns dictated by the comet's rotation and internal structure. Unlike diffuse cometary activity where the entire sunlit surface sublimates more or less uniformly, these cryovolcanic plumes emerge from specific source regions, creating the spiral structures visible in high-resolution imagery. This is not entirely unprecedented. We have observed cryovolcanism elsewhere in our solar system. Saturn's moon Enceladus famously sprays geysers of water ice from fractures near its south pole. Neptune's moon Triton shows evidence of nitrogen geysers. Pluto may have cryovolcanic features as well, but all of those objects orbit within our solar system. They formed from the same primordial disk of gas and dust that created our sun and planets. They are, in a cosmic sense, our siblings. 3I Atlas is not our sibling. It is a stranger from an entirely different family, born around a different star, shaped by processes we can only speculate about. And yet, it is displaying cryovolcanic activity that we can recognize and relate to phenomena in our own cosmic backyard. What does this tell us? First, it confirms that the basic physics of ice behavior is universal. The same phase transitions, the same thermodynamic principles, operate in other solar systems just as they do here. Carbon dioxide ice sublimates at similar temperatures regardless of which star it formed around. Water ice behaves the same way whether it condensed in our protoplanetary disk or in a nebula halfway across the galaxy. This universality is reassuring. It means our understanding of planetary science translates to alien worlds. Second, and more intriguingly, the spectral analysis conducted alongside the cryovolcanism study revealed striking similarities between 3I Atlas and a class of objects in our own solar system called trans-Neptunian objects, or TNOs. These are the frozen bodies that orbit beyond Neptune, in the cold outer reaches where solar heating is minimal. Pluto's the most famous TNO, but thousands more have been catalogued, ranging from small icy fragments to dwarf planets. The researchers found that the chemical fingerprints of 3I Atlas closely match those of primitive meteorites called CR carbonaceous chondrites, which are thought to represent some of the oldest, most unaltered material in our solar system. They also found similarities to TNOs, suggesting that despite coming from another star entirely, 3I Atlas is made of fundamentally similar stuff to the frozen bodies at the edge of our own system. This is a profound finding. It implies that the building blocks of planetary systems may be universal across the galaxy. The same types of ices, the same types of rocky materials, the same types of organic compounds may form around countless stars, producing objects that look remarkably similar regardless of their origin. If true, this has enormous implications for the search for life. If the raw ingredients are the same everywhere, then the chemical pathways that led to life on Earth may be operating throughout the cosmos. 3I Atlas is not just a curiosity, it is a data point in the most important scientific question humanity has ever asked. Are we alone? But there is another aspect of the cryovolcanism discovery that has received less attention, and it is this aspect that some researchers find troubling: the spiral pattern of the jets. When material erupts from a rotating body, it traces patterns determined by the rotation rate, the ejection velocity, and the geometry of the source regions. For a simple rotating object with random vents, you would expect chaotic, irregular patterns. What the observations show is something more organised. The jets appear to follow coherent spiral structures, suggesting either very specific internal geology or, more controversially, a highly uniform rotation state. One analysis of the imagery, conducted by independent amateur astronomers and shared widely online, claims to identify dual clockwise spin waves in the coma structure. If confirmed, this would indicate an extremely stable rotation axis and a remarkably consistent internal structure. Natural comets typically have chaotic rotation states, tumbling and wobbling as asymmetric outgassing torques their nuclei in unpredictable ways. A stable, organised rotation producing symmetric spiral jets would be unusual. Now, I need to be careful here. This analysis has not been peer-reviewed. It is based on images that require significant processing to reveal subtle details, and processing can introduce artifacts. The researchers who published the cryovolcanism preprint have not endorsed claims of unusual rotational signatures, and there are natural mechanisms that could produce organised jet structures, including unusual internal geology or tidally locked rotation. But the observation exists, the images exist, and they add another item to the growing list of things about 3I Atlas that do not quite fit the standard model. Let me describe what cryovolcanism actually looks like, so you can understand what observers are reporting. Imagine a chunk of ice several kilometres across, dark as charcoal on its surface due to billions of years of cosmic ray bombardment. As it approaches the sun, that surface begins to warm. The outer layers, saturated with carbon dioxide ice, start to sublimate. Gas escapes, carrying dust particles with it. This creates the fuzzy coma that surrounds the nucleus, but beneath the surface, the heating is uneven. Some regions are more porous. Some contain pockets of more volatile ices. As the heat penetrates, it reaches these reservoirs. The pressure builds, and then suddenly a vent opens. Gas and dust rocket outward in a focused jet, travelling at hundreds of meters per second. The jet emerges from a specific spot on the surface, and as the comet rotates, that spot traces an arc across the sky like a garden sprinkler. Multiple vents produce multiple jets. Their patterns interweave, creating the complex structures visible in long exposure images. And if the rotation is stable, and the vents are arranged in certain configurations, those patterns can take on spiral forms that repeat with mathematical regularity. The question is whether the patterns observed in 3I Atlas are consistent with random vent placement on a naturally formed object, or whether they suggest something more structured. It is too early to say definitively. The data is still being analysed. But the fact that this question is even being asked about an object that mainstream science insists is just a comet illustrates how unusual 3I Atlas truly is. What can we expect to learn as the comet approaches closest approach? As 3I Atlas continues to recede from the Sun, its activity should gradually decline. The surface heating that drives sublimation will weaken. The jets should become less energetic. The coma should fade. This is the normal pattern for comets post-perihelion, but the key word is should. 3I Atlas has not consistently followed the patterns we expect. Its brightness evolution has been unusual, its structural integrity has been remarkable, and there is no guarantee that its behaviour over the next 2 weeks will match our predictions. Researchers are particularly interested in watching for changes in activity level as the comet passes through different distance thresholds. Certain volatile ices sublimate at specific temperatures, so as the comet cools, we should see changes in the composition of its emissions. Water ice, for example, is more volatile than carbon dioxide at these distances, so water production might increase relative to CO2 as the comet moves farther from the Sun. The James Webb Space Telescope is scheduled to observe 3I Atlas with its infrared instruments, which can identify specific molecules by their spectral signatures. These observations will provide the most detailed chemical inventory yet of an interstellar object. If there are unusual compounds present, if the chemistry deviates from what we expect, Webb will reveal it. Ground-based observers will continue monitoring the visual appearance, watching for changes in the tail structure, the jet patterns, and the overall brightness. Any sudden outbursts or unexpected fragmentation would be immediately noticed and reported. And amateur astronomers around the world will be contributing their own observations, adding to the global dataset that professional researchers draw upon. Some of the most important discoveries in cometary science have come from amateur observers who noticed something the professionals missed. With thousands of eyes watching 3I Atlas through the closest approach window, the odds of catching unexpected behaviour are maximised. What would convince mainstream science that 3I Atlas is not natural? This is a question that deserves an honest answer. The default assumption is natural origin, and extraordinary claims require extraordinary evidence. What would that evidence look like? A major trajectory change not attributable to outgassing would be almost impossible to explain naturally. If 3I Atlas suddenly altered course in a way that violated conservation of momentum, that would be definitive. Artificial light emissions, distinct from sunlight reflection or fluorescence, would be similarly conclusive. If the object began glowing in patterns or wavelengths inconsistent with natural processes, that would demand explanation. Radio transmissions correlated with the object's position would be powerful evidence. In fact, the Meerkat Radio Telescope in South Africa has already searched for narrowband signals from 3I Atlas. They found nothing, establishing an upper limit equivalent to the power output of a mobile phone at that distance. But the search continues. Structural revelations that expose obviously manufactured components would be definitive, but we are unlikely to get images detailed enough to reveal such features given the object's distance. Short of these smoking guns, we are left with accumulating circumstantial evidence. Each anomaly that cannot be explained adds to the case for something unusual. But no amount of anomalies reaches the threshold of proof. There is always another natural explanation to invoke, however strained it might become. This is the situation we find ourselves in. An object that behaves almost but not quite, like a comet. An object that displays feature after feature that demands explanation. An object that has sparked more scientific controversy in 5 months than any astronomical discovery in recent memory. And now, as we speak, new images are arriving from a spacecraft that was never designed for this mission but seized the opportunity to observe something extraordinary. The European Space Agency's JUICE mission has given us our first glimpse of 3I Atlas from beyond Earth's orbit, and what those images reveal has only deepened the mystery. The JUICE revelation and the hidden tales. Sometimes the most important discoveries come from instruments that were never designed for the task. The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, launched in April of 2023 on an 8-year journey to study Europa, Ganymede, and Callisto. It was built to probe the ice-covered oceans of these alien worlds, searching for environments that might harbour life. Nobody expected it to photograph an interstellar comet. But the universe does not care about mission parameters. When 3i Atlas was discovered in July 2025, mission planners at ESA realized they had a unique opportunity. JUICE was positioned roughly 60 million kilometers from the comet's trajectory, far closer than any Earth-based observatory during the critical post-perihelion period. While telescopes on our planet strained to see the comet through the sun's glare, JUICE had a clear view. Between November 2nd and November 25th, the spacecraft devoted observing time to 3i Atlas, using 5 scientific instruments. Cameras, spectrometers, and particle sensors all turned toward this unexpected target. The data they collected represents some of the most valuable observations of any interstellar object ever made. But there was a problem. JUICE is currently using its main high-gain antenna as a heat shield, protecting the spacecraft from solar radiation during this phase of its journey. Without that main antenna available for communication, data can only be transmitted to Earth through a smaller backup antenna at drastically reduced rates. The full data set from the 3i Atlas observations will not arrive on Earth until February of 2026. 3 months. 3 months before we see what JUICE really captured. But the scientists were impatient, and so, as a teaser, they downloaded just a quarter of a single image from the spacecraft's navigation camera. One partial image from one instrument, taken on November 2nd, 2 days before JUICE's closest approach to the comet. Even in that fragmentary glimpse, 3i Atlas revealed something remarkable. 2 tails. The image shows the comet clearly, its bright coma glowing against the blackness of space, but extending from that coma are not one but 2 distinct structures. A plasma tail of ionized gas stretches in one direction, pushed by the solar wind into a narrow stream of charged particles. A fainter dust tail extends in a different direction, composed of tiny solid particles that respond more slowly to solar radiation pressure. Dual tails are not unprecedented for comets. In fact, most active comets display both a dust tail and an ion tail under the right conditions. The ions respond almost immediately to the solar wind, creating a straight, narrow tail that always points directly away from the sun. The dust particles are heavier and take longer to accelerate, creating a curved tail that trails behind the comet along its orbit. When viewing geometries favourable, both tails are visible separately. So why is this significant? Because the appearance of both tails confirms that 3i Atlas was extremely active when JUICE observed it. The comet was vigorously outgassing both gas, which becomes ionized and forms the plasma tail, and dust, which forms the separate dust tail. This level of activity, just days after perihelion, indicates that the nucleus was responding intensely to solar heating. But more importantly, the geometry and relative brightness of the 2 tails will provide crucial information about the comet's composition and activity mechanisms. Once the full dataset arrives in February, researchers will be able to analyze the spectral signatures of each tail separately, identifying specific molecules in the gas component and characterizing the particle sizes in the dust component. The plasma tail, in particular, carries chemical information about the comet's volatile content. Different molecules ionize differently and emit light at characteristic wavelengths. By studying the plasma tail spectrum, scientists can determine what ices are sublimating from the nucleus. Previous observations have already shown that 3i Atlas is unusually rich in carbon dioxide compared to solar system comets. The JUICE data will refine these measurements and potentially reveal additional chemical species. The dust tail tells a different story. Dust particle sizes, compositions, and ejection velocities can all be inferred from the tail's appearance and how it changes over time. For 3i Atlas, the dust tail is particularly interesting because of the anti-tail phenomenon we discussed earlier. The presence of large dust particles, ejected sunward and only slowly swept back by radiation pressure, creates the unusual forward-pointing feature that has attracted so much attention. But here is what makes the JUICE observation truly invaluable. The spacecraft's viewpoint was fundamentally different from any Earth-based telescope. When we observe 3i Atlas from Earth, we see it from a specific angle determined by our planet's position in its orbit. That viewing geometry affects everything: the apparent shape of the coma, the orientation of the tails, the visibility of different features. Certain structures might be invisible from Earth simply because of how they are oriented relative to our line of sight. JUICE observed from a different position in space, 60 million kilometers away from Earth's viewpoint. This provides a stereoscopic baseline, like having a second eye that sees the same object from a different angle. By combining Earth-based observations with JUICE observations, researchers can reconstruct the three-dimensional structure of the coma and tails in ways that would be impossible from a single vantage point. This multi-point observation campaign is unprecedented for an interstellar object. When Oumuamua passed through our solar system in 2017, we had only a few weeks to observe it, and no spacecraft positioned for a different perspective. When Borisov visited in 2019, we had more time but still only Earth-based views. 3i Atlas is the first interstellar visitor to be studied from multiple points across the solar system simultaneously. The scientific value of this coordinated observation campaign cannot be overstated. We are assembling a three-dimensional model of an object from another star system, tracking its behavior as it responded to solar heating, and tracing the evolution of its activity over months. No previous interstellar object has been characterized this thoroughly, and yet the JUICE teaser image also raises questions. Look closely at descriptions of the image. The plasma tail extends upward, the dust tail trails off to the lower left, but some analysts have noted what appear to be additional structures, faint extensions that do not quite fit the simple two-tail model. Are these imaging artifacts, debris from fragmentation, jets from localized activity, or something else entirely? We will not know until February. Until then, we can only speculate. What we do know is that 3i Atlas was surprising in its activity level. The JUICE team used the word surprised when describing what the navigation camera revealed. They had expected to see a comet post-perihelion, yes, but the intensity of the activity, the brightness of the coma, the clarity of the dual tail structure exceeded expectations for an object already receding from the Sun. This ties back to one of the anomalies we discussed earlier. 3i Atlas brightened faster than models predicted as it approached perihelion, and it has remained brighter than expected afterward. Its activity curve does not match the standard templates derived from observing solar system comets. There are natural explanations for this. Perhaps 3i Atlas has a higher proportion of volatile ices than typical comets. Perhaps its surface is more porous, allowing heat to penetrate more deeply and mobilize subsurface materials. Perhaps billions of years of cosmic ray bombardment created a unique surface chemistry that responds differently to solar heating. All of these explanations are plausible. None of them are confirmed. The JUICE mission was not the only spacecraft to observe 3i Atlas from a unique vantage point. NASA's fleet of planetary exploration missions contributed their own observations. The Mars Reconnaissance Orbiter, using its high-rise camera, captured images when the comet passed within 19 million miles of the red planet. The Perseverance rover on the Martian surface looked up with its cameras and photographed this interstellar visitor in the Martian sky. The MAVEN spacecraft, designed to study Mars's atmosphere, collected spectral data on the comet's emissions. Each of these observations came from a different location, adding to our multi-point picture of the object. ESA's ExoMars Trace Gas Orbiter contributed additional data, and the combined Mars observations allowed researchers to improve predictions of 3i Atlas's trajectory by a factor of 10 compared to Earth-only measurements. This trajectory refinement is more important than it might seem. For an interstellar object moving at over 150,000 miles per hour, small uncertainties in position translate to large uncertainties in future location. By precisely tracking 3i Atlas's path, researchers can predict where it will be weeks and months from now with much greater accuracy. Why does that matter? It matters because any unexpected changes to that trajectory would be immediately detectable. If 3i Atlas deviates from its predicted path in ways that outgassing cannot explain, we will notice. If it performs a maneuver, we will see it. So far, the trajectory has followed predictions within expected tolerances. The non-gravitational acceleration observed at perihelion was consistent with intense cometary outgassing. There have been no unexplained course changes, but the observation window is not closed. The comet is still being tracked, and December 19th, the day of closest Earth approach, will provide our best opportunity for precise measurement before the object recedes too far for detailed observation. What happens after JUICE data arrives in February? The scientific analysis will take months, possibly years. High-resolution spectroscopy will reveal the detailed chemical composition of the comet's emissions. Particle data will characterize the dust grain sizes and distributions. Camera images will be processed to extract every possible detail about the nucleus and coma structure. Comparisons will be made to solar system comets to Oumuamua, to Borisov, to theoretical models of interstellar objects. Papers will be written, debates will be had, our understanding of what 3i Atlas is and where it came from will gradually sharpen. But some questions may never be answered definitively. We cannot land on 3i Atlas. We cannot send a probe to study it up close. It is moving too fast, and there was too little time to mount an intercept mission. By the time we knew this object existed, it was already past the point where any existing technology could catch up to it. We get one chance. These observations, spread across months but concentrated in this window around closest approach, are all we will ever have. 3i Atlas will pass Jupiter in March 2026 and then vanish back into interstellar space, carrying its secrets with it. Whatever we learn now. Whatever questions remain unanswered when it leaves, remain unanswered forever. And that is what makes the controversy over the images so frustrating. Because while scientists wait for data and debate interpretations, a parallel drama has been unfolding that calls into question the very institutions we rely on for information. When NASA finally held its press conference after the government shutdown ended, revealing images collected by spacecraft across the solar system, the response from some quarters was not gratitude but suspicion. The images were blurry, the details were limited, and amateur astronomers, working with backyard telescopes, seemed to be producing clearer views than billion-dollar spacecraft. Was NASA hiding something? Or were expectations simply misaligned with reality? The answer to that question reveals something important about how we process information in an age of instant access and perpetual skepticism. NASA's blurry secret or amateur astronomers' triumph. The government shutdown lasted 43 days. From mid-October through late November, NASA went silent. No press conferences, no image releases, no official commentary on the interstellar object that was captivating the world's attention. 3i Atlas passed through perihelion, emerged from behind the Sun, and began its approach toward Earth, all while the agency responsible for studying it could not even issue a statement. This silence created a vacuum, and into that vacuum rushed speculation, conspiracy theories, and a growing suspicion that something was being hidden. When NASA finally resumed operations and announced a press conference for November 19th, anticipation was intense. For over a month, amateur astronomers and foreign space agencies had been the only sources of new imagery. The European Space Agency had released observations from their Mars orbiters. Independent astrophotographers had captured the comet from backyard observatories. Professor Avi Loeb had been posting daily analyses of amateur images, cataloguing anomalies, and raising questions that NASA could not answer. The press conference was supposed to change everything. NASA would reveal what its spacecraft had seen during the critical perihelion period. High-resolution images from the most sophisticated instruments in the solar system would finally settle the debates. We would know, once and for all, what 3i Atlas really looked like. What we got instead was a fuzzy white dot. The clearest image NASA presented came from the HiRISE camera on the Mars Reconnaissance Orbiter, the most powerful imaging system ever sent to another planet. HiRISE can resolve objects on the Martian surface smaller than a meter across. It routinely produces images of stunning detail. But 3i Atlas was not on the Martian surface. It was 19 million miles away when HiRISE captured it, and at that distance, even the most advanced camera produces only a small smudge of light. The public reaction was immediate and intense. Social media erupted with accusations. How could amateur astronomers with backyard telescopes produce clearer images than a billion-dollar space agency? Why was NASA showing us blobs when independent observers were capturing tail structure and coma details? What was being hidden? The controversy reached mainstream news coverage. Articles appeared contrasting amateur images, which showed recognizable comet features, with NASA's offerings, which looked like out-of-focus stars. Critics pointed to this discrepancy as evidence of deliberate obfuscation. Surely NASA had better images and was choosing not to release them. The reality is more mundane, but also more instructive. NASA's spacecraft were not designed to photograph distant comets. The HiRISE camera is optimized for close-range imaging of planetary surfaces, not for resolving faint objects millions of miles away. Its extraordinary resolution is achieved by being close to the target, not by having unusually large optics. When pointed at something as distant as 3i Atlas, it becomes essentially a small telescope, comparable in capability to ground-based instruments. Amateur astronomers, meanwhile, were using techniques optimized for exactly this kind of observation. Long exposures, sometimes spanning hours, stacked together to accumulate signal. Tracking systems that followed the comet's motion rather than the background stars. Processing algorithms that enhanced contrast and revealed subtle features. The images that looked better from amateur observers were not raw single frames. They were the product of sophisticated processing applied to accumulated data. When NASA scientists apply similar techniques to their raw data, the results improve dramatically. But the press conference showed preliminary images, quickly processed to meet public demand, not the final polished products that would emerge after months of careful analysis. This is how science works. Raw data rarely looks impressive. The beautiful images we associate with Hubble or Webb are the result of extensive processing, color mapping, and careful presentation. Initial releases prioritize speed over aesthetics, but explanations do not travel as fast as accusations. The narrative that NASA was hiding something took hold and spread. Professor Loeb amplified the criticism, arguing that the agency should have emphasized what we do not understand about 3I Atlas, rather than insisting it is a familiar comet. He had a point, if not about cover-ups, then about communication. The press conference tone was defensive, almost dismissive. When Associate Administrator Amit Kshatriya opened with the statement that this object is a comet, it looks and behaves like a comet, and all evidence points toward it being a comet, he was technically correct, but rhetorically tone-deaf. People did not tune in to be told to stop asking questions. They tuned in to see what NASA had discovered. The contrast between institutional messaging and independent analysis has been a recurring theme throughout the 3I Atlas event. NASA emphasizes the known, the understood, the comfortable. It assures the public that there is no danger, no mystery, nothing to worry about. Independent researchers emphasize the anomalies, the questions, the possibilities. They invite the public to wonder. Neither approach is entirely honest. NASA's certainty is performative. Behind closed doors, scientists are as puzzled by the anomalies as anyone. Papers are being written exploring unusual explanations. Debates are happening in academic channels, but the public-facing message is reassurance. Do not panic, it is just a comet. Meanwhile, some independent analysts overstate the evidence for artificial origin. The probability calculations Loeb presents are estimates based on assumptions that may not hold. The anomalies, while real, may have natural explanations we have not thought of yet. Emphasizing mystery sells books and generates clicks, but it can also mislead audiences about the actual state of scientific knowledge. The truth, as usual, is somewhere in between. 3I Atlas is unusual, more unusual than NASA's public messaging acknowledges, less certainly artificial than some breathless coverage suggests, but here is what gets lost in the institutional versus independent debate. The amateurs are contributing real science. Images captured by backyard astronomers have revealed features in 3I Atlas that professional observatories initially missed. The evolution of the tail structure over days and weeks has been documented through thousands of independent observations. The spiral jet patterns that spark the cryovolcanism interpretation were first noted in amateur images before being confirmed by larger telescopes. This is not unprecedented. Amateur astronomers have been contributing to cometary science for decades. They discover new comets, track brightness changes, and provide the kind of sustained monitoring that professional observatories, with their limited telescope time and competing priorities, cannot always maintain. What is new is the sophistication of amateur equipment. Smart telescopes with automated tracking and stacking produce results that rival professional observatories from a generation ago. High-quality CCD cameras capture details invisible to the photographic plates of the past. Online communities share techniques and data, allowing rapid improvement in observational methods. The democratization of astronomy means that when something like 3I Atlas appears, thousands of capable observers are ready to contribute. The global network of amateur astronomers has become a scientific instrument in its own right, and some of those amateurs have captured images that professional scientists find genuinely puzzling. Between November 22nd and 24th, astronomers in Japan, Spain and Chile independently photographed 3I Atlas with remarkably consistent results. Their images showed a defined coma structure, a narrow tail extending over 600,000 miles, and what appeared to be a conical shape to the nuclear region. Professor Loeb shared these images widely, noting that they provided clearer views than the official NASA releases. He pointed to the anti-tail, still visible weeks after perihelion, as evidence of unusual dust dynamics. He highlighted apparent structural features in the coma that suggested organised activity rather than random outgassing. Were these features real or artifacts of processing? The debate continues. Different analysts reach different conclusions depending on how they interpret the data. Without access to the original raw files, it is difficult to assess which features are genuine and which are introduced by image stacking and enhancement algorithms. This is the fundamental challenge of observing faint objects at great distances. The signal is weak. The noise is strong. Every technique we use to extract information from the data also introduces potential artifacts. Distinguishing real features from processing ghosts requires expertise, skepticism, and often independent confirmation. For 3i Atlas, independent confirmation has been possible because so many observers are watching simultaneously. When the same feature appears in images from Japan and Spain and Chile, captured by different equipment using different techniques, confidence increases that the feature is real. When a feature appears in only one dataset, it is more likely to be an artifact. The spiral jet structures have been confirmed by multiple independent observers. The anti-tail has been confirmed. The dual-tail structure seen by JUICE has been confirmed. These are real features of a real object. What remains debated is the interpretation of these features. Natural cometary activity or something else? The institutional position is clear. NASA, ESA, and the vast majority of professional astronomers consider 3i Atlas to be an unusual but natural interstellar comet. Its anomalies are explained by invoking unfamiliar compositions and histories, not artificial origin. The alternative position, championed primarily by Loeb, but supported by a small number of other researchers, holds that the accumulating anomalies warrant serious consideration of a technological hypothesis. Not proof, not certainty, just serious consideration. Both positions are defensible. Both may be wrong. What is indefensible is refusing to look. What is indefensible is declaring certainty when mysteries remain. What is indefensible is dismissing questions simply because the answers might be uncomfortable. The amateur astronomers who have contributed so much to our understanding of 3i Atlas understand this instinctively. They look because they are curious. They share because they want to know. They question because that is what science demands. As we approach December 19th, the debate will only intensify. More images will arrive. More analyses will be published. More anomalies may emerge, or existing ones may be explained. But one thing has already been demonstrated. The barrier between professional and amateur has never been lower. The ability of ordinary people to contribute to extraordinary discoveries has never been greater. And when the institutions we rely on for information fail to communicate clearly, the public now has alternatives. 3i Atlas has not just visited our solar system, it has transformed how we observe the cosmos. And yet, for all the controversy over images and institutions, one question looms larger than all others. The question that drew millions of people to follow this story in the first place. The question that refuses to be dismissed no matter how often experts pronounce it answered. Is 3i Atlas a comet from another star? Or could it be something that only looks like a comet? The mothership hypothesis has been called ridiculous, irresponsible, and unscientific. It has also been called thought-provoking, important, and overdue. What it cannot be called is resolved, because the evidence that would definitively rule it out has not materialized, and the evidence that would definitively confirm it has not appeared either. We are left in that uncomfortable middle ground where certainty is impossible and the stakes are too high to simply look away. The mothership hypothesis on trial. Let me be direct about something. The vast majority of scientists believe 3i Atlas is a comet. They believe this not because they lack imagination, but because the evidence points in that direction. The object has a coma, it has tails, it is outgassing water and carbon dioxide. It follows a trajectory consistent with gravitational physics, plus minor perturbations from that outgassing. Everything we see is consistent with an unusual but natural interstellar visitor. When Professor Avi Loeb suggests that 3i Atlas might be an alien mothership, he is making a claim that contradicts the professional consensus of his field. That does not make him wrong. Consensus has been wrong before. but it does mean the burden of proof rests heavily on those proposing the extraordinary explanation. So let us examine the mothership hypothesis on its own terms. What would it mean if 3i Atlas were artificial? What evidence would support that conclusion? And what evidence would contradict it? The core of Loeb's argument is probabilistic. He looks at the accumulated anomalies, assigns rough probabilities to each one occurring by chance, and multiplies them together to get a combined probability. If each anomaly has a 1 in 100 chance of occurring naturally, and there are 10 independent anomalies, the combined probability drops to 1 in 10 billion billion. Numbers that small suggest something other than chance is at work. This is a valid form of reasoning when applied correctly. Scientists use similar logic when claiming detection of new particles at facilities like the Large Hadron Collider. If the data shows a signal that would occur by random fluctuation less than 1 in 3 million times, they claim a discovery. But the logic has pitfalls. The anomalies must be genuinely independent. If they are correlated, if one anomaly makes another more likely, then multiplying probabilities gives misleading results. And the baseline probabilities must be estimated correctly. If we do not know how often interstellar comets have unusual nickel ratios, assigning a probability to that observation becomes guesswork. Critics of Loeb's calculations point to exactly these issues. The anomalies are not independent. An unusual composition might lead to unusual activity which produces unusual tails. Correlation reduces the effective number of independent data points, and our sample size of interstellar objects is 3. We simply do not know what range of behaviours is normal for such visitors. This criticism is fair but not conclusive. Even accounting for correlations and uncertainties, 3i Atlas remains an outlier. Whether that makes it suspicious enough to warrant considering artificial origin is a judgment call that reasonable scientists can disagree on. Let us consider what an artificial interstellar probe might look like if it were designed by an advanced civilization. Science fiction has given us many visions of alien spacecraft. Gleaming metal hulls, glowing engines, geometric precision. But a civilization capable of interstellar travel would likely be far more sophisticated than anything Hollywood imagines. They might have very different design philosophies, and crucially, they might have reasons to avoid detection. The Trojan horse scenario suggests that an alien probe might disguise itself as a natural object. Cover a technological core with ice and rock debris. Mimic the behaviour of a comet. Pass through foreign solar systems unnoticed. Observing without being observed. This is not a wild speculation. It follows logically from strategic considerations that any intelligence might face. If you do not know whether the civilizations you encounter will be friendly or hostile, minimizing your visibility is prudent. An alien spacecraft that looked obviously artificial might trigger defensive responses. One that looked like a comet would be ignored. Under this scenario, the anomalies we observe in 3i Atlas could be imperfect mimicry. A technological object trying to look natural but not quite succeeding. The unusual chemistry, the strange activity patterns, the anti-tail, all could be artifacts of the disguise rather than natural variation, or they could be exactly what they appear to be. Unusual features of an unusual comet. How would we distinguish between these possibilities? The most definitive test would be observing clearly artificial behaviour, a major trajectory change not attributable to outgassing, artificial light emissions, radio transmissions, the release of subprobes. Any of these would be impossible to explain naturally and would force even skeptics to reconsider. So far, none of these have been observed. The Meerkat radio telescope searched for narrowband signals from 3i Atlas in early November. They scanned frequencies that SETI researchers consider optimal for interstellar communication. They found nothing. The upper limit they established was equivalent to about the power output of a mobile phone at the comet's distance. If 3i Atlas were transmitting, it was doing so more quietly than we can detect. The trajectory has remained consistent with gravitational physics plus cometry, outgassing. No unexpected manoeuvres, no course corrections that cannot be explained by jets pushing the nucleus around. No artificial lights have been detected, no structural features that suggest manufactured components. By these measures, 3i Atlas passes the test for a natural object. It has not done anything that a comet could not do. But absence of evidence is not evidence of absence. A sufficiently advanced technology might be undetectable by definition. A probe designed for stealth, would not transmit radio signals or perform obvious maneuvers. It would look exactly like what we see, a comet. This is the frustrating epistemological trap of the Trojan horse hypothesis. If aliens are clever enough to disguise their probes, they are clever enough to avoid detection by our current instruments. We cannot prove a negative. We cannot demonstrate that 3i Atlas is natural with the same certainty that we could demonstrate it is artificial if it performed an unmistakable technological act. Loeb assigns about a 30 to 40% probability that 3i Atlas is not fully natural. This number represents his personal judgment based on the accumulated anomalies. Other scientists would assign far lower probabilities. Some would say effectively zero. The numbers reflect assumptions and priors more than objective measurement. What I find most interesting about the mothership hypothesis is not whether it is correct, but what it reveals about scientific culture. Loeb has been criticised harshly for even suggesting artificial origin. Colleagues have called his ideas ridiculous, nonsense, and insulting to legitimate research. The intensity of this reaction seems disproportionate to the actual claims being made. After all, Loeb is not saying 3i Atlas is definitely alien. He is saying there is a non-negligible probability that deserves consideration. He is saying we should keep an open mind until the evidence conclusively points one way or the other. He is saying that extraordinary events, however improbable, have enormous consequences and should not be dismissed reflexively. These seem like reasonable scientific positions, yet they have generated extraordinary hostility. Part of the hostility is professional. Loeb promotes his ideas aggressively, seeking media attention and public engagement in ways that many academics find distasteful. He has been accused of seeking fame rather than truth, of prioritizing headlines over rigor. Part of the hostility is protective. Scientists who study exoplanets in CT worry that wild claims about alien spacecraft make their entire field look foolish. They fear that association with sensational hypotheses will damage funding and credibility for legitimate research, and part of the hostility is psychological. The possibility of alien intelligence is deeply unsettling. If 3i Atlas were artificial, it would mean we are not alone, that other intelligences exist, that they are capable of reaching our solar system. The implications cascade through religion, philosophy, security, and human self-conception. Dismissing the hypothesis protects us from confronting those implications. Whatever the motivation, the result is a scientific culture that discourages certain questions, not officially, not formally, but through social pressure and professional consequences. Loeb has tenure at Harvard. He can say what he wants without losing his job. But younger researchers, those still building careers, observe how he is treated and draw conclusions. Better to stay quiet. Better to stay safe. This dynamic is worth noting regardless of whether 3i Atlas is natural or artificial. Science advances by questioning assumptions. If certain questions become socially unacceptable, progress slows. Let me offer a thought experiment. Suppose 3i Atlas is natural, just an unusual comet from another star. In that case, Loeb's hypothesis is wrong, but asking the question was still valuable. It prompted more careful observation. It forced researchers to articulate why they believe what they believe. It engaged the public in scientific thinking. Now suppose 3i Atlas is artificial. In that case, the dismissive reaction from mainstream science looks catastrophically foolish. We had an alien probe in our solar system, and we refused to consider the possibility because it seemed too strange. The expected value calculation favours taking the hypothesis seriously, even if the probability is low. The cost of being wrong if it is natural is minimal embarrassment. The cost of being wrong if it is artificial is missing the most important discovery in human history. This is why I refuse to simply accept the institutional reassurance that 3i Atlas is just a comet. Not because I believe it is alien, not because I have evidence that contradicts the consensus, but because the stakes are too high for lazy certainty. We should watch, we should measure, we should question. We should remain open to surprise while demanding rigorous evidence, and we should recognize that whatever 3i Atlas is, our brief encounter with it has already revealed something important about ourselves, about how we process the unknown, about how institutions manage uncomfortable possibilities, about how the public engages with science that touches on our deepest questions. December 19th approaches. The comet draws closer, and somewhere in the data already collected but not yet analysed, there may be answers we have not imagined. But before we reach that climactic closest approach, we need to consider one more piece of evidence, or rather, one more absence of evidence, because the silence from 3i Atlas is itself a form of information. The radio frequencies we have searched, the signals we have not detected, the cosmic quiet that may mean nothing at all, or may mean everything. What the radio silence really means. On November 5th, 2025, one of the most sensitive radio telescopes on Earth turned its array toward an interstellar visitor. The Meerkat facility in South Africa, 64 dishes spread across the Karoo Desert, focused on the coordinates of 3i Atlas and listened. They were searching for technosignatures, narrowband radio emissions that could not be produced by natural processes, the kind of signal that a technological civilization might generate, intentionally or otherwise, the kind of signal that would transform our understanding of our place in the universe. They found nothing. Well, that is not entirely accurate. They found plenty of signals, 23,689 of them, to be precise. But every single one was traced back to human sources, radio frequency interference from our own technology, reflecting off satellites and bouncing through the ionosphere, Earth calling Earth, echoing in the cosmic static. From 3i Atlas itself, silence. Nothing but the whisper of cosmic background radiation and the occasional chirp of a pulsar rotating somewhere in the distant galaxy. The detection limit they established was remarkable. If 3i Atlas were transmitting radio waves at power levels equivalent to a mobile phone, at frequencies between 900 and 1670 MHz, the Meerkat array would have heard it. That is an extraordinarily sensitive threshold. A mobile phone operates at around 1 watt. At a distance of 334 million kilometers, which is how far 3i Atlas was during the observation, detecting 1 watt of radio emission is like hearing a whisper from across an ocean. So what does this silence mean? The most straightforward interpretation is that 3i Atlas is not transmitting, because there is nothing to transmit. It is a comet. Comets do not have radio transmitters. Natural objects are naturally quiet in the radio spectrum except for thermal emission and occasional molecular line radiation, neither of which would produce the narrowband signals SETI researchers look for. Under this interpretation, the Meerkat null result is exactly what we should expect, and provides no information one way or the other about the object's nature. We did not detect artificial signals because there were no artificial signals to detect. But consider the alternative. Suppose 3i Atlas were a technological object. Would we expect it to be transmitting radio signals that Meerkat could detect? Not necessarily. A probe from an advanced civilization might have very good reasons to remain radio silent. Stealth considerations, for one. If you are sending an observation platform into a foreign solar system, you probably want it to observe without being observed. Blasting radio signals announces your presence to anyone listening. A wise designer would build a probe that operates passively, collecting data through sensors but not transmitting anything that could give it away. Interstellar distances create another complication. 3i Atlas has travelled for billions of years between star systems. During that time, whatever civilization launched it might have ceased to exist. There might be no one to transmit to. A probe could be programmed to remain silent unless it detects signals worth responding to. Or it might have a narrow transmission beam pointed away from Earth, communicating with some relay station we cannot see. The physics of interstellar communication also matters. Radio waves are not particularly efficient for spanning light years. They spread out, losing power with the square of distance. An advanced civilization might use entirely different methods, lasers, gravity waves, technologies we have not conceived. Our radio telescopes could be as useful for detecting their communications as a butterfly net would be for catching radio waves. So the Meerkat null result constrains the hypothesis space but does not eliminate the technological possibility. If 3i Atlas were an alien probe deliberately trying to avoid detection, or using communication methods we cannot intercept, we would observe exactly what we did observe. Nothing. This is the recurring challenge with SETI research. Null results are ambiguous. They could mean no one is there. They could mean someone is there but is not talking. They could mean someone is talking but in ways we cannot hear. What would it take to make a positive detection? The classic SETI scenario involves a powerful narrowband signal at a specific frequency that cannot be produced naturally. The hydrogen line at 1420 MHz is a favourite candidate because hydrogen is the most common element in the universe, and any technologically sophisticated civilization would likely be aware of its spectral significance. A strong signal at that frequency, coming from the direction of an interstellar object, would be extraordinary. Other frequencies have been proposed. The waterhole, the range between hydrogen and hydroxyl lines, where radio interference is minimal. Mathematical frequencies, multiples of fundamental constants that would signal intentional design. The electromagnetic spectrum is vast, and we can only search tiny slices of it at any time. Meerkat searched a substantial range, from 900 to 1670 MHz, covering the hydrogen line and surrounding frequencies, but that still leaves most of the radio spectrum unexamined, and it leaves optical, infrared, and other portions of the electromagnetic spectrum entirely untouched. Other searches have been conducted as well. The Breakthrough Listen initiative, the largest SETI program in history, has directed resources toward 3i Atlas. Various university groups and independent researchers have pointed their instruments at the object. So far, no confirmed detections. But again, absence of evidence is not evidence of absence. We are searching with the tools we have, looking for the signals we know how to recognize. An alien civilization with billions of years of technological development might communicate in ways as incomprehensible to us as a smartphone would be to a medieval peasant. Consider another aspect of the radio silence. 3i Atlas is producing substantial emissions of gas and dust. Water molecules, carbon dioxide, various volatiles are streaming off the nucleus and into the coma. Some of these molecules emit at radio wavelengths as they are excited by solar radiation. This natural emission creates a baseline level of radioactivity from any active comet. 3i Atlas's natural radio emission could potentially be detected if it was strong enough. The Meerkat observations focused on narrowband artificial signals rather than the broadband natural emission, but other instruments might detect molecular spectral lines. In fact, the Meerkat team reported detecting hydroxyl, OH, molecules associated with the comet, produced when solar ultraviolet light breaks apart water escaping from the surface. This detection is significant. It represents the first radio detection of molecular species from an interstellar comet. The hydroxyl absorption feature confirms that 3i Atlas is actively outgassing water, consistent with its cometary nature. But it raises a question for the technological hypothesis. If 3i Atlas were a disguised probe, presumably it would want to mimic natural cometary behavior. Producing outgassing that contains water and hydroxyl would be part of that mimicry. The radio detection of natural molecular species does not distinguish between a real comet and a fake one. What would distinguish them? Anomalies in the molecular ratios, potentially. If the chemistry of the outgassing were inconsistent with known cometary compositions, that might suggest artificial origin. But 3i Atlas's chemistry, while unusual in some respects like the high carbon dioxide content and nickel abundance, falls within the range that could plausibly result from natural variation among interstellar objects. Artificial structures embedded in the radio signal would be distinctive. If the molecular emission showed modulations or patterns that encoded information, that would be very difficult to explain naturally. But no such patterns have been detected. The fundamental limitation is that we do not know what we are looking for. We search for radio signals because we use radio signals. We search for narrowband emissions because our technology produces narrowband emissions. But we are projecting our own technological paradigm onto hypothetical aliens who might think entirely differently. This is sometimes called the streetlight effect, named for the joke about a drunk searching for lost keys under a streetlight, because that is where the light is, not because that is where the keys were dropped. We search where we can search, but the signals might be somewhere else entirely. Loeb has argued that the proper response to this uncertainty is not to give up but to search more broadly. Develop new detection methods. Look for signatures we have not looked for before. Treat interstellar objects as potential technological artifacts until proven otherwise, rather than dismissing the possibility without investigation. This approach has merit. If we never look for alien technology, we will never find it, even if it exists. The cost of searching is modest. The potential payoff is enormous. But it also creates a problem. If we cannot define what we are looking for, we cannot know when we have found it. The list of anomalies around 3i Atlas grows because we do not have a clear model of what a natural interstellar comet should look like. Every unexpected observation gets flagged as potentially significant, but unexpected observations are expected when we are seeing something for only the third time. The meerkat radio search was valuable regardless of outcome. It established limits. It demonstrated that if 3i Atlas is communicating by radio, it is doing so very quietly or on frequencies we did not examine. Future searches can build on this baseline, extending the frequency range, improving sensitivity, watching for changes over time. As 3i Atlas approaches Earth for its closest approach on December 19th, additional radio observations are planned. The greater proximity will improve sensitivity slightly, though the improvement is marginal compared to the distances involved. More importantly, the geometry will change, potentially revealing signals that were beamed in directions we could not intercept earlier. And after closest approach, as the comet recedes toward Jupiter, something else becomes possible. If 3i Atlas were to perform a Jupiter-Oberth maneuver, using the giant planet's gravity to alter course or deploy smaller probes, the timing would create opportunities for radio detection. Any communication between a mothership and its probes might be interceptable during the months around the Jupiter encounter in March 2026. This is speculative in the extreme, but it illustrates how the observation window extends beyond December. The story of 3i Atlas is not over when it passes closest to Earth. It continues as long as we can track the object and as long as the possibility of unexpected behavior remains. The silence so far tells us that 3i Atlas is not broadcasting obvious radio signals at the power levels and frequencies we searched. It does not tell us whether the object is natural or artificial. It does not resolve the debate that has consumed the astronomical community for months. What it does tell us is that we are paying attention. For the first time in history, humanity has a coordinated global effort to study an interstellar visitor in real time. We are searching for techno-signatures. We are monitoring for anomalies. We are ready as we can be, for the unexpected. If 3i Atlas is just a comet, this vigilance costs us nothing and teaches us much about an ancient messenger from another star. If it is something more, we will not miss it through inattention. That, in the end, may be the most important outcome of the 3i Atlas event, regardless of what the object turns out to be. We have practiced. We have coordinated. We have demonstrated that when something unusual appears in our cosmic neighborhood, we can mobilize resources and attention at a global scale. The next interstellar object may be even stranger, and next time we will be better prepared. But before we look to the future, we need to address one more present mystery. The trajectory that takes 3i Atlas not away from the Sun, in a simple hyperbolic arc, but directly toward the largest planet in our solar system. The encounter with Jupiter in March 2026, and the disturbing precision with which that encounter has been calculated. The Jupiter maneuver theory. Of all the anomalies catalogued for 3i Atlas, the 13th may be the most unsettling. Not because it is the strangest, but because it requires us to think about what happens after the spotlight moves on. After December 19th, after the world's telescopes turn to other targets, after most people have forgotten that an interstellar visitor ever passed through our neighborhood, 3i Atlas is not leaving the solar system in a straight line. Its hyperbolic trajectory curves through the gravitational field of the Sun, yes, but it also passes remarkably close to Jupiter on March 16th, 2026. The distance of closest approach has been calculated with increasing precision as observations accumulate. Currently, the best estimates place it at approximately 53 million kilometers. That number would be unremarkable except for one thing. It almost exactly matches Jupiter's Hill radius. The Hill radius is a concept from celestial mechanics that defines the region around a massive body, where that body's gravity dominates over the gravity of a more distant but larger body. For Jupiter orbiting the Sun, the Hill radius is about 53.5 million kilometers. Within that distance, Jupiter can capture satellites. Beyond it, the Sun's influence takes over. The match is precise to within about 60,000 kilometers, 1 part in 1,000. Professor Loeb identified this coincidence and calculated the probability of it occurring by chance. His estimate, roughly 1 in 26,000. Not impossible. But combined with the other improbabilities already associated with 3i Atlas, another item for the growing list of things that do not quite fit. Why does this matter? If you wanted to use a planet's gravity to perform a maneuver, to brake or accelerate or change direction, the optimal approach distance is near the Hill radius. Too far, and you get minimal gravitational effect. Too close, and you risk capture or collision. The Sweet spot is right at the edge of gravitational dominance. This is called an Oberth maneuver, named after the rocket pioneer Hermann Oberth, who described the physics in the early 20th century. Spacecraft use gravity assists routinely to gain or lose velocity. Voyager used Jupiter's gravity to accelerate toward the outer solar system. Juno used it to slow down and enter Jupiter orbit. The technique is standard in mission design. For an interstellar object on a hyperbolic trajectory, a gravity assist at Jupiter could serve multiple purposes. It could boost the object's exit velocity, sending it out of the solar system faster. It could alter the trajectory, bending the path in a new direction. Or, most intriguingly from a certain perspective, it could serve as an optimal point for deploying smaller objects. A mothership releasing probes near a gas giant makes strategic sense. The probes could enter orbit around Jupiter or its moons. They could use the planet's gravitational influence to scatter in different directions. They could observe the outer solar system's largest planet, whose atmospheric dynamics and magnetic environment might be visible from interstellar distances and thus serve as a navigation beacon. This is speculation, pure speculation. There is no evidence that 3I Atlas will do anything at Jupiter other than fly past on its way out of the solar system. The trajectory has been consistent with gravitational physics. No maneuvers have been observed. The Hill radius coincidence could easily be random chance. But the speculation illustrates something important. Even after closest Earth approach, even after the excitement of December fades, 3I Atlas will continue to be scientifically significant. The Jupiter encounter in March 2026 represents another observation opportunity, another chance to detect anomalous behaviour, another window during which the unexpected might reveal itself. The Juno spacecraft is currently orbiting Jupiter. When 3I Atlas passes within 53 million kilometres, Juno will be relatively nearby compared to Earth-based telescopes. Mission planners are already considering whether to dedicate observation time to the interstellar visitor. The instruments on Juno were designed to study Jupiter's atmosphere, magnetic field and interior structure. They were not designed for comet observation, but like the Mars orbiters that photographed 3I Atlas during its close approach to the red planet, Juno might contribute valuable data from a unique vantage point. The geometry of the Jupiter encounter also provides natural experiments. As 3I Atlas passes through Jupiter's magnetosphere, the interaction between cometary ions and the planet's magnetic field could reveal information about the comet's composition and outgassing rates. Any unusual behaviour, any deviation from what models predict, would be detectable. And if 3I Atlas were to perform a manoeuvre, that would be the moment. The perihelion-Oberth window has passed. The comet emerged from its closest solar approach, behaving exactly as expected, no surprises, no course corrections. But Jupiter offers a second opportunity. A probe designer who wanted to minimize detection risk might wait until the object is far from Earth, far from the concentrated attention of our telescopes, before activating propulsion systems. This is the scenario that Loeb has called the Trojan horse delay, an artificial object maintaining its disguise through the inner solar system when every telescope is watching, then revealing its true nature in the outer system when attention has waned. Is this likely? No. The balance of evidence strongly favours a natural comet. But is it possible? Yes. And because it is possible, responsible observation continues. Let me describe what the Jupiter encounter will look like from an astronomical perspective. By March 2026, 3I Atlas will have faded significantly. Its activity will have declined as it recedes from the sun and cools. The bright coma and tails visible now will become fainter, harder to observe. Only the largest ground-based telescopes and space observatories will be able to track it. The comet's brightness at Jupiter distance is estimated to be magnitude 15 or fainter, invisible to all but the most capable instruments. Amateur astronomers who captured beautiful images during the December closest approach will no longer be able to contribute. The observation will fall entirely to professional facilities. This creates a potential gap in monitoring. If something unusual were to happen during the Jupiter encounter, would anyone notice? The answer depends on how many observatories commit time to tracking an object that, by then, will seem like old news. Loeb has advocated for continued monitoring specifically because of this concern. He argues that the Jupiter encounter deserves as much attention as the current closest Earth approach. The possibility of deployment of probes or gravitational maneuvers, however remote, should be taken seriously enough to justify dedicated observation time. Whether his advocacy will succeed in securing telescope allocations remains to be seen. Competition for observation time is fierce. There will be other targets, other discoveries, other demands on limited resources. 3i Atlas may slip into the outer darkness unwatched, or it may not. The ESA JUICE spacecraft, currently en route to Jupiter, will arrive in the Jupiter system in 2031. While it will not be able to observe the March 2026 encounter directly, its path through interplanetary space might still provide useful observations if mission planners choose to allocate time. More immediately, the intense study of 3i Atlas during its current closest approach is generating data that will take years to fully analyse. The JUICE observations from November will not arrive on Earth until February. The James Webb Space Telescope data requires extensive processing. The thousands of amateur observations need to be compiled, calibrated, and compared. Scientific understanding of 3i Atlas will continue to evolve long after the object itself has departed. Papers will be published, debates will continue, anomalies will either be explained or will remain on the list of unresolved mysteries. And here is a thought that keeps some researchers awake at night. What if the Jupiter encounter does reveal something unexpected? What if 3i Atlas performs a maneuver, or releases smaller objects, or does something else that cannot be explained by natural processes? By then, the object will be billions of kilometers away, receding at tremendous speed. There will be no possibility of sending a follow-up mission, no opportunity to get a closer look. Whatever we learn from light that has travelled for hours across the void. We would have confirmation that we are not alone. We would have evidence of technology from another civilization, and we would watch it disappear into the interstellar darkness, carrying answers we desperately want but cannot reach. This is why some argue for an interceptor mission concept, a spacecraft design that could be launched on short notice to catch up with an interstellar object. The technology does not currently exist. Our fastest probe, the Parker Solar Probe, travels at around 430,000 miles per hour near the Sun, but even that is far too slow to catch an object moving at 150,000 miles per hour and accelerating away from us. But future technology might close the gap. Solar sails accelerated by powerful lasers, nuclear propulsion systems, advanced concepts that could reach interstellar velocities. If such a capability existed, we could potentially send a probe to rendezvous with an interstellar visitor, photograph it up close, analyse its composition, and definitively answer whether it is natural or artificial. 3i Atlas is lost to us. We cannot catch it. But the next interstellar object might be within reach if we develop the capability in time. This is one of the legacies of the 3i Atlas event. It has highlighted how unprepared we are for interstellar visitors. We had only months of warning before the object plunged toward the Sun and emerged on the other side, heading for the outer system. We had no means to study it up close, no way to intercept it, no plan for what to do if it turned out to be extraordinary. The next time might be different, or it might be exactly the same. We might have another tantalizing glimpse of something that could be alien technology, watch it slip away beyond our reach, and spend decades wondering what we missed. The universe does not owe us clear answers. It does not arrange encounters for our convenience. 3i Atlas arrived when it arrived, followed the trajectory physics dictated, and will leave when physics says it must leave. We are observers, privileged to witness but powerless to intervene. What we can do is watch. What we can do is record. What we can do is think carefully about what we see and what it might mean. December 19th is 14 days away as of this recording, the moment of closest approach, the peak of the observation window, the best chance we will ever have to understand this messenger from the void. After that, the long, slow fade. The Jupiter encounter in March, the gradual dimming as 3i Atlas recedes toward interstellar space, and then nothing. Empty space where a visitor used to be. Memories and data and unanswered questions. Unless something changes, unless the object surprises us, unless the universe delivers one more twist before this strange chapter closes, the countdown continues. 14 days until closest approach. 14 days to watch, to wonder, to prepare for whatever comes next. And in those 14 days, we must ask ourselves a final question. Not about 3i Atlas, but about us. About what this encounter has revealed about humanity. About what message we are sending to the cosmos, whether anyone is listening or not. December 19th, and the message in a bottle 7 billion years. That is how long 3i Atlas may have been travelling through the universe before it arrived in our solar system. 7 billion years of cold, silent drifting through the space between stars. 7 billion years before there was an Earth to visit, before there were humans to wonder about it, before there was anyone at all to notice a small chunk of ice and rock passing through the cosmic void. The Sun itself is only 4.6 billion years old. 3i Atlas, if the estimates are correct, was already ancient when our star first ignited. It was already old when the disk of gas and dust that became our planets began to collapse. It was already carrying whatever secrets it carries for billions of years before the first bacteria appeared on Earth. We are not just looking at a comet, we are looking at a time capsule from an epoch so remote that it predates everything we know. Every mountain on Earth, every ocean, every fossil buried in every rock, everything we have ever studied or discovered or wondered about, all of it came after 3i Atlas was already wandering the galaxy. And now, for a few brief months, its path intersects with ours. A cosmic coincidence, a chance alignment of trajectories across unimaginable distances and incomprehensible timescales. We get to see it. We get to study it. We get to ask what it is and where it came from and what it means. This is the privilege of being alive at this moment in history. Not just witnessing an interstellar visitor, but witnessing the third one, the biggest one, the most active and most studied and most debated. A visitor that has forced us to confront questions we thought were purely theoretical. Are we alone? Is the universe full of natural debris? Or could something more purposeful be moving among the stars? What would alien technology look like if it existed? How would we recognize it? How would we respond? These questions existed before 3i Atlas. They will exist after it is gone. But for these few months, they have taken on an urgency and a specificity that transforms abstract philosophy into practical observation. We are not just imagining contact scenarios. We are actually searching for techno-signatures in an actual object that actually came from another star. That is extraordinary, regardless of what 3i Atlas turns out to be. Let me paint a picture of December 19th. The sun will rise as it always does, indifferent to the cosmic drama unfolding hundreds of millions of miles away. People will go to work, eat breakfast, argue about politics, scroll through social media, live their ordinary lives largely unaware that something ancient is passing nearby. But for those who know, for those who care, the day will feel different. A sense of something momentous, even if that something is too distant to see without a telescope, too far to touch, too fast to catch. In observatories around the world, astronomers will be at their instruments. The Virtual Telescope project in Italy will be streaming live. Professional facilities in Hawaii, Chile, Australia, the Canary Islands will be gathering data. Amateur astronomers in their backyards, huddled against the December cold, will be pointing their telescopes at Leo and looking for a faint fuzzy patch beneath the bright star Regulus. The James Webb Space Telescope, floating 1 million miles from Earth at the L2 Lagrange point, will turn its golden mirror toward an object from another star. The Hubble Space Telescope, still working after 3 decades, will capture images that will be analysed for years to come, from Earth, from Mars orbit, from spacecraft scattered across the inner solar system. Eyes both electronic and organic will watch 3i Atlas reach its closest point to our planet. 1.8 astronomical units, 270 million kilometres, nearly twice the distance from Earth to the Sun. Not close, in human terms. If 3i Atlas were visible to the naked eye, it would be a faint dot, indistinguishable from thousands of other faint dots in the night sky. But in cosmic terms, this is a near miss. The object that has travelled for billions of years across trillions of kilometres is passing within shouting distance, cosmically speaking. And then it will keep going. That is the part that catches in the throat, the impermanence of it all. 3i Atlas does not stop for us. It does not pause to be examined. It does not wait while we debate its nature or prepare better instruments or summon the will to send a probe. It comes, it passes, it goes. By January it will be noticeably dimmer. By March, only the largest telescopes will track it as it approaches Jupiter. By summer, it will have faded beyond detection for all but the most specialised instruments. And within a few years, it will be gone entirely. A memory, a data set, a mystery that may never be fully solved. What will we have learned? We will have learned that interstellar comets are more common than we thought. The detection of 3 objects in just 8 years, after millions of years of human history with no detections, tells us that the Vera Rubin Observatory, coming online soon, will find many more. This was not a once-and-forever event. It was a preview of a new era of discovery. We will have learned that objects from other star systems share chemical kinship with objects in our own. The presence of water, carbon dioxide, and familiar molecular species in 3I Atlas suggests that the building blocks of planetary systems are universal, the same ingredients that made our solar system exist around other stars. We will have learned that interstellar objects can survive billions of years in the cold void and still become active when they encounter a star. The cryovolcanism observed on 3I Atlas demonstrates that pristine ancient ice can erupt when heated, releasing material that has been locked away since before our sun existed. We will have learned how to coordinate global observation of unexpected phenomena. The response to 3I Atlas, despite government shutdowns and institutional friction, demonstrated that the scientific community can mobilize rapidly when something important appears. We will be better prepared next time, and we will have learned something about ourselves, about our capacity for wonder and our tendency toward paranoia, about our hunger for meaning and our resistance to uncertainty, about how we process information that touches on our deepest questions about our place in the universe. The debate over 3I Atlas will not end on December 19th. It will not end when the object fades from view. It may not end for decades. The anomalies that have been catalogued will either be explained or will remain as persistent mysteries, fuel for speculation and research alike. Some will remember 3I Atlas as proof that we are not alone, even if definitive evidence was never found. The coincidences were too many, the anomalies too strange, the feeling of presence too strong to dismiss. Others will remember it as a beautiful example of how unusual natural objects can appear artificial to those primed to see technology everywhere. A lesson in pattern recognition, in the dangers of motivated reasoning, in the importance of maintaining scientific skepticism even when the alternative is more exciting. Both perspectives have merit. Both will shape how we approach the next interstellar visitor, and the next one, and the one after that. The universe is vast and old and strange. It contains wonders we have not imagined and horrors we cannot conceive. It may be teeming with intelligence, or it may be empty, a cosmic desert in which we are the only minds contemplating the stars. We do not know, we may never know, but we can look, we can wonder. We can reach out across the void with our telescopes and our radio dishes and our earnest curiosity, searching for signs that someone else is out there, that we are not alone in this immense darkness. 3I Atlas is leaving. Whatever it is leaving, and we must let it go. But we do not have to let go of what it taught us. We do not have to forget the questions it raised or the possibilities it illuminated. We can carry those forward into the next discovery and the one after that. The universe sends us messages, not in words, not in signals we immediately understand, but in objects and phenomena that challenge our assumptions. 3I Atlas is such a message, a bottle from a distant shore, washing up on our cosmic beach after billions of years at sea. We cannot read the message yet, we may never read it fully, but we can hold the bottle, we can examine it from every angle, we can wonder who sent it and why. That is enough. That is more than enough. That is the great privilege of consciousness in a universe that mostly does not have any. Thank you for taking this journey with me. Thank you for your curiosity, your patience, your willingness to sit with uncertainty and wonder together about things that may never be fully answered. If this exploration has meant something to you, I hope you will share it with others who might find value in it. A like, a subscribe, a comment telling me where you are and what you think. These small gestures help build a community of curious minds reaching toward the stars. And I want to remind you, as I always do, that what we have discussed here is a blend of established science and informed speculation. The mainstream scientific consensus holds that 3I Atlas is a natural interstellar comet. The alternative hypotheses we explored are minority positions, thought experiments, possibilities rather than probabilities. I encourage you to read widely, think critically, and form your own conclusions based on evidence rather than authority. The cosmos does not care about our opinions. It simply is what it is, vast and ancient and indifferent to our debates. Our task is to understand it as best we can, with humility and rigour and an openness to being surprised. December 19th approaches, the countdown continues, and somewhere out there, beyond the orbit of Mars and falling ever deeper into the outer darkness, a piece of another star system carries its secrets toward the edge of the knowable and beyond. Watch the skies, keep wondering, and sleep well, knowing that the universe, in all its terrifying grandeur, has noticed us enough to send a visitor, even if only in passing. Good night, wherever you are, and clear skies.